I'm Phil Massey. I'm an astronomer here at Lowell Observatory. I'm going to be talking to you today about how stars work. So you go outside at night and look at the sky, and you see hundreds, maybe even a couple thousand of these twinkling little objects. What are they? How did we find out what they were? Richard Feynman, the physicist, has said that if civilization collapsed and there was only one fact that he could convey to the descendants, that information would be the atomic hypothesis, the idea that all things are made out of atoms that move around in motion, attracting each other when they're a little distance apart, but repelling each other when they're squeezed into one another. By the way, we'll be touching on that point in a little bit. I would add to that the fact that the stars are very different suns. How did we find this out? Well, the first written suggestion of this was by Anaxagoras, a Greek living around 450 BC. And in a contemporary account, what's written is that he had said that one of the largest things in the universe is a hot stone that we call the sun. When Anaxagoras was very young, he predicted that sooner or later a piece of the sun would break off and fall to the earth. 20 years ago, they wrote, he was proved right. The whole world saw a fragment of the sun fall in a fiery arc through the sky. When the fiery fragment cooled, it proved to be nothing more than a chunk of brown rock. Overnight, Anaxagoras was famous. Today, his book is read everywhere, they wrote. You could buy a secondhand copy in Angora for a drachma. So, of course, today we know that what they saw fall to the ground was actually a meteorite. But he was the first to suggest, or at least the first person that we have a record of to suggest that the stars were distant suns. For this, he has a crater on the moon named after him. The next time this was suggested publicly was by the Italian Bruno. In 1584, he argued that the stars were suns with planets of their own. For this, he was burned at the stake in 1600. So both of these people, their argument for the stars being distant suns, they were philosophical in nature. They weren't really scientific. Oh, Bruno also has a crater named after him on the moon. The first scientific evidence that the stars were distant suns actually came about by Friedrich Bessel. Bessel is well known and loved by physics students the world over for what's known as the Bessel equation, which is a way of describing the harmonic distortion that happens when you beat a drum. But in 1837, Bessel measured the parallax of 61 Cygni. Now, parallax, if you hold your finger up to near your nose and you open one eye and then you open the other eye, closing the first, and you do this, you can see your finger move back and forth against the background. And that's the same phenomenon, that's the same way, that's called parallax. And the same thing happens if you're in a car and you're seeing nearby trees that are moving relative to the more distant background mountains. So as the Earth goes around the sun from one side to the other in 6 months, if you're looking at a relatively nearby star, relative to the more distant stars, you will see a positional change. Over here in January, they'll see it over here. But in July, you'll see it over here. Now, because the stars are so far away, these motions are very small. And he picked 61 Cygni. Now, 61 Cygni is a very obscure star, but he had spent most of his career measuring the positions of stars very, very accurately, visually with a telescope and a micrometer. And what he had discovered was that some stars were moving relative to the stellar background, not due to parallax, but just a steady motion. And he had found that 61 Cygni had a very large proper motion. If you think that all the stars are sort of moving at about the same speed in random directions, which they're not, but just imagine it that way, then the ones that are nearer to you are going to have the larger angular displacement in a year. So 61 Cygni had a large angular displacement, which suggested it was relatively nearby, and therefore it would be easier to measure its parallax. It was also a double star, making it easier to make a precise measurement with the instruments that Bessel had at his disposal. Basically, a little eyepiece with a spider web across it as a crosshair that would allow him to split the difference in location. And the parallax he measured was 1/3 of an arcsecond, which translates to 10 light years, 61 trillion miles. So when we say the star was nearby, we mean relatively nearby. Now, this is a very small angular change, 1/3 of an arcsecond. That's the size of a dime at a distance of 8 miles. But this demonstrated then that the stars must be distant suns. At that distances, their brightness would be consistent with them being the same intrinsic brightness as the sun. And of course, Bessel got a crater named after him as well on the moon. So the implications were that stars were suns, but at vast distances. Little sidebar, how do we know the distance to the sun? Because we can't measure directly by parallax. What we did know was the relative distances of the sun and the planets, just from Kepler's law of planetary motions, which I won't go into. But it means that we knew that Mars, when at its closest approach, was 1.52 times as far from the sun as the Earth is. Just another 0.52, what we would call an astronomical unit away. And what we could do was measure the parallax of Mars. And the first accurate measurement of the parallax of Mars was made in 1672 by Riker and Cassini from Paris and Seine. Seine is a small town in South America in French Guiana. It's sort of to the north of Brazil and to the east of Venezuela. And this measurement was actually good to 10%. And so suddenly we knew the absolute size of things in the solar system back in the late 1600s. A more accurate way of measuring the parallax, the distance to the sun, is from the transit of Venus. Now, many of you may have seen the Venus transit that happened about 10 years ago now, that was quite visible from North America. The transits of Venus happen usually in pairs, and they don't occur very often. They occur maybe once or twice a century. Dozens of astronomers were deployed around the world for the Venus transits in 1761 and 1769 in order to measure the length of the chord, how long it took Venus to cross the sun. If you did that from several different places on the Earth and you knew the distance between those places, then you could get the distance to Venus and the distance to the sun, again, from simple geometry. James Cook was involved in this, making measurements for Tahiti. Astronomers were distributed around the world, and the resulting values were good to 2%. I'm sorry to say that not all the astronomers survived this Lowell adventure. As you can imagine, travel around the world in the mid-1700s was not quite as easy as it is today, or at least was 6 months ago. So how do stars work? We know now that there are things like the sun, but how does the sun work? What if the sun was a big ball of burning coal and oxygen? If you had the optimal mixture of coal and oxygen, then given the brightness of the sun would last for 1,500 years. So we know that's not the right answer, because the Romans would have mentioned if there was no sun around. So we know the sun has been around a lot longer than that. And in fact, in 1862, Lord Kelvin calculated the Earth was 20 to 400 million years old. He did this based on the idea that the Earth was originally molten and had cooled down to its current temperature. If you calculated how long that would take, that would be somewhere between 20 and 400 million years. The problem with that calculation is that it ignored two important facts. One is there's radioactive material inside the Earth, which provides an important heating source. And secondly, there's convection. The mantle is thermally unstable, and so you're moving hot material from deeper in the Earth and to nearer the surface. In 1895, John Percy modeled the mantle and convection and concluded that 3 billion years was a much more likely number, but everyone pretty much ignored that. At this point, along came Madame Marie Curie, and her work on radioactivity basically changed everything. For one thing, it was an additional source of heating that Kelvin had ignored since he didn't know about it, and it opened up the ability to do radioactive dating. For this, she not only has a crater named after her on the moon, but she has one named after her on the planet Mars as well. Along came Hermann von Helmholtz, who tried to address how the sun could shine. And he had two theories. The first explanation he offered was maybe enough meteors and space debris were hitting the sun that just the kinetic energy, the energy of that motion and the impact is what kept the sun shining. And there were two problems with that. The first problem was it would require 100 trillion tons of matter per hour to fall on the sun. And so that seemed a rather unlikely large number. The other problem is the sun's mass would keep increasing. If the sun's mass increased, the Earth would the year would be shorter and shorter, as the length of the year would depends upon how much mass there is in the sun and our distance from the sun. And the Earth's year would be getting 2 seconds shorter every year if this was the explanation. And even at this time, the late 1800s, we were able to measure the length of the year well enough so that we knew that the year wasn't getting 2 seconds shorter every year. The second explanation really caught on, and that was the idea that the sun could be contracting. If the sun was contracting, then just the gravitational potential energy could explain the luminosity, the brightness, the heat and light that the sun gives off. It would just have to contract an inch for every 3 hours, and that would provide enough energy. However, this really would only allow the sun and the Earth to have existed for 100 million years, because 100 million years ago, the sun would have been that big. Okay. And this conflicted with what geologists and evolutionary biologists knew, but it was consistent with other thoughts about the age of the Earth. And so for 50 years, this became the prevalent notion. Physicists sort of dismissed the geologists and the evolutionary biologists. After all, that's all kind of soft science. And so the thinking was, okay, the stars and the sun, they all worked by gravitational collapse. For this, Helmholtz also has a crater named after him. In the early 1900s, Albert Einstein came along, and in 1905, he derived the mass energy equivalence. Also in the early 1900s, atomic physics was coming into its own. Radioactivity turns out to be just one form of nuclear energy. Ernest Rutherford, who's been described as the father of atomic physics, in 1917, Rutherford bombarded atoms of nitrogen with helium nuclei, and this produced oxygen and hydrogen atoms. This was finally transmutation, the goal of alchemists for thousands of years. He had produced elements from other elements simply by bombarding nitrogen with helium atoms. This was the first lab example of nuclear fusion, the first demonstration that you could actually cram atoms together and make new elements. For this, Rutherford also has a crater on the moon, this small one here, and also a crater on Mars named for him. William Hawkins had earlier suggested that 4 hydrogen atoms could be fused into an atom of helium. Now, one helium atom has a tiny bit less mass. It weighs a little bit less, just 0.7% than 4 hydrogen atoms. But this difference in mass matters. Remember, E equals mc squared. So the mass difference then is really small. But c in this equation is the speed of light. And if you take, and the speed of light is a really big number. And if you take a really big number and multiply it by itself, it becomes an even much bigger number. And so you would get a lot of energy just from the small amount of mass. The only problem with this is you needed special conditions to fuse atoms. Remember that Feynman quote at the beginning. He noted that when atoms came close together, they like to repel each other. And in order to cram atoms together to do nuclear fusion, you would need incredibly high temperatures, temperatures of millions of degrees. We knew that the sun's temperature was only thousands of degrees. And how do we know that? Well, we knew that from its color. If I were to take this very, very fine coffee cup, and I wouldn't do this, and heat it up to a temperature of 5,700 degrees Kelvin, it would glow with the same color as the sun glows. It would have the same surface temperature as the sun, and it would emit the same light as the sun. It would be the same color as the sun. If you look at your toaster when it's on, you'll see that the coils are glowing red. Don't stick a knife in there with it still on, but they're glowing red. And that is because those coils are at a temperature of several thousand degrees. And if you heated them up a little bit more, they would be the same color as the star Betelgeuse, a cool red supergiant. So we knew the temperature of the sun, or at least we knew the temperature at the surface of the sun. So it didn't seem as if nuclear fusion could be operating in stars until Arthur Eddington came along. What Eddington asked the question, what if the sun isn't collapsing? What if the sun were stable? What would that imply? And there's an equation that students of stellar structure learn in their first class, and that's the equation of what's called hydrostatic equilibrium. And what this differential equation simply says is, actually, it's a very easy concept, which is if you have a big ball of gas, like say the sun, then in order to hold up the outermost layer, you don't need very high temperature or pressure. There's not very much pushing down on you. But if you were near the center of the sun, you would have the weight of all that material above you. And the only way you could support that would be if you had very high temperatures and very high pressures. Eddington assumed that the sun was what's called an ideal gas, a perfect gas. And then just from this equation and some boundary conditions, he calculated that the central temperature of the sun would be 20 million degrees. If you do the calculation much more carefully, you get that the central temperature is 15 million degrees. 15 million degrees, 20 million degrees. There's no difference there. It's enough to do nuclear fusion. And so suddenly, we had a potential explanation. However, this explanation hinges on the assumption that wasn't known yet, that 5% of the sun, at least 5% of the sun was hydrogen. If 5% of the sun was hydrogen, you could fuse it into helium, and that would provide enough energy to power the sun for billions of years. He got a crater named after him too. So what keeps the stars shining is nuclear fusion in their cores. That is a viable explanation. For most of a star's life, this fusion is in the form of 4 hydrogen atoms being turned into 1 helium atoms. But to know if this could possibly be correct, we had to answer another question. And that question is, what are stars made of? And I'm going to explain how we found that out. So Sir Isaac Newton took a prism and passed sunlight through it, and he got this nice little spectrum. This rainbow color, same rainbow that you see when from water droplets when it's rained recently and the sun is behind you. If Sir Isaac had had a better instrument, he would have seen what Fraunhofer later saw, which is that the spectrum of the sun is not just a continuous rainbow, but it has these dark bands, these bands where light is missing. And it was possible to identify what was causing these bands by doing experiments in the laboratory. If you took gas and you passed light through it and passed that through a prism, you could see if the same color was missing. These missing colors, these missing wavelengths are like fingerprints. And in fact, this line is due to hydrogen, this line is due to sodium, this line is due to iron, this line is due to hydrogen, that line is due to hydrogen. These two lines here, H and K, the strongest lines in the spectrum of the sun, are actually due to calcium. So we know that these elements are present in the sun, but we don't know in what proportion. I mean, could be that the sun is mainly made out of milk. So Fraunhofer not only got a crater named after him, but he got a postage stamp in his honor. What about other stars? Well, Annie J. Cannon is probably the most important, and certainly one of the most important astronomers of the 20th century. What she did was she classified the spectra of tens of thousands of stars. I'm going to show you examples of 4 different types of stars. This is a spectrum of an O-type star. It's the kind of star that I work on. And next week, Catherine Nugent is going to be giving a talk on massive stars, and she's going to talk about O stars and Wolf-Rayet stars. And so these stars show hydrogen and helium lines in their spectrum, and really nothing else, not much else. Helium, by the way, was discovered in the sun. We didn't know, we had not identified it in the laboratory in our atmosphere yet, but it was an unknown feature in the spectrum of the sun, and that's why it's called helium, for Helios, meaning the sun. This is an A-type star. This would be a star like Vega. And it has, if you look at its optical spectrum and you don't look too carefully, all you see are lines of hydrogen. So we know that Vega has hydrogen. By the time we get to the spectrum of a star like the sun, a G-type star, we see hydrogen, but we also see iron, we see calcium. Seems like all these stars might be made of something different. And finally, if we go to a star like Betelgeuse, an M-type star, we see calcium lines, and we also see molecules of titanium oxide. This is used in very reflective white paint. Maybe Betelgeuse is mainly made of white paint. We don't know yet. So Annie J. Cannon classified stars based on their spectra. And for this, she not only has a crater named after her, she not only has a Delaware coin commemorating her, she not only was a Google icon on the 150th anniversary of her birth, but she also has one of the most prestigious prizes in astronomy named after her, the Annie Jump Cannon Award. And the first recipient of that award is this woman, Cecilia Payne. And she did her PhD thesis. It says here at Harvard, but of course, Harvard wouldn't let women in those years complete a degree, do a graduate degree. And so she had to be enrolled in Radcliffe, which was sort of part of Harvard. And she did her PhD thesis with a Harvard thesis advisor. And in 1925, she did the remarkable thing of combining the results of Annie J. Cannon's observations of the stars with this new theory of atomic physics. And combining these led her to realize that the difference in the spectra of stars was not their composition, that all stars were pretty much made of exactly the same material in the same proportions, not completely, we'll get to that, but pretty close. And that the thing that changed was different between an O star and a G star and an A star and an M star. This was purely temperature. The second thing that she discovered was stars were composed primarily of hydrogen and helium and only a tiny bit of everything else. Now, a very influential astronomer during this time period, I must first tell you the story because it had a big effect on my career. One of the things that Cecilia Payne wrote was, only become an astronomer if nothing else will satisfy you, because nothing else is approximately what you will receive. The material returns will never be great, and most of the scholars who receive them do so at the price of sacrificing time that they might devote to pure scholarship. If you do your job, you'll be able to earn your living, and you will taste the delights of discovery than which, to the addict, there is nothing more satisfying. That is all. If that's enough, then become a scientist. If it's not, get out before it's too late. I think this is good advice to graduate students, that they go into this field with their eyes open. And it's true, we have everything that we want from a material point of view. We're able to, buy groceries and everything. But what I'm getting out of astronomy is this thing that she talks about here, this little addiction, that we find out things, and for a little while, you're the only person who knows this new thing about the universe. And then, of course, you quickly want to write it up for publication so that you can share this information with others. Well, first you share it with your co-authors and your colleagues, but then you share it with everyone. Well, when she went to share, she had a problem, and that was a very influential astronomer named Henry Norris Russell did not believe her results about the stars being primarily hydrogen and helium. He was okay with the idea that the stars were all roughly the same material, but he convinced Cecilia Payne to describe her results about hydrogen and helium as being spurious. When she published her thesis, this was the word she used. But she didn't really believe that, I don't think. Now, Henry Norris Russell is mostly known for the Hertzsprung-Russell diagram, which is a plot of brightness versus spectral class, or absolute magnitude versus temperature or luminosity. In other words, something to do with how bright the star is and how hot the star is. And it allows astronomers to organize stars so that we understand what's a supergiant and what's a giant and what's a main sequence. But what Russell should be most noted for was a paper in 1929, a couple of years after Cecilia Payne did her thesis, on the composition of the sun's atmosphere. And in this, he realizes that he was wrong, that he does a similar sort of analysis to what Cecilia Payne did for stars. He does it for the sun, and he gets the same answer that she got. And he was honest enough to put this in the paper. He compares his results to, as he puts it, Miss Payne's in this table. And he says, this is very gratifying agreement, especially when it is considered that Miss Payne's results were determined by a different theoretical method with instruments of quite different type, and even on different bodies, a long list of stars, almost all of which are giants. And he finds almost the exact same thing now for the sun. So suddenly we know that 90% of the stars are made of hydrogen, 9% of helium, and 1% is basically everything else by numbers. I'm now going to describe the evolution of the sun a little bit. Now, when astronomers use certain words, we mean them differently than the way that everyone else uses them. For instance, to an astronomer, a metal is anything that's not hydrogen and helium. In the same way, we talk about the evolution of the sun or the evolution of stars, but we don't mean evolution the way a biologist means evolution. Evolution to a biologist means how species change, how they adapt to new things and change over time. But we're now talking about more how a star ages. How does the sun age is more what we mean when we talk about solar evolution. So core hydrogen fusion will run for 10 billion years. The sun will be getting brighter and brighter. It's about 30% brighter now than it was when the Earth first formed. By the time we hit 10 billion years, it's going to be 70% brighter than it is now. Hydrogen burning, eventually you use up the hydrogen in the core of the star, where the temperature is high enough for nuclear fusion. The sun will collapse a little bit, and it will heat up enough so that you can do nuclear fusion in the core in a shell around this inert helium core. The surface then begins to expand, and the core contracts as the sun enters its red giant phase. When it enters the red giant phase, this is very bad for the Earth. Well, it's very bad for Mercury. You can see right now, this is the size of the sun. This is how big the sun will be as a red giant. It will extend well past the orbit of Mercury, most of the way to the orbit of Venus. And here will be the Earth, and the Earth will be pretty much a burnt cinder at this point. I'm now going to show this evolution a little bit on what's called a Hertzsprung-Russell diagram, in which we start off at point A. This is now a logarithmic scale, so that this means if the sun were here, it would be 10 times brighter than here. So the sun starts out, and right now we're defining 0 as being how bright the sun is now. So the sun starts off less luminous than it is now. It's going to get more luminous, and then at point C, it starts turning into a red giant, and it vastly expands till it gets up to here at F, where the helium in the core suddenly undergoes nuclear fusion itself, converting the helium into carbon. The sun then does, over a very short period of time, a little dance in this diagram, becoming what's called an asymptotic giant branch star. And then it zips over to the hot end of the HR diagram. These are now times in thousands of years, just 100,000 years after being an asymptotic giant branch star. It becomes the central star of a planetary nebula, and then starts becoming a white dwarf. If we were to plot this another way, so that we now can see time along the x-axis and luminosity along the y-axis, this is where the sun is now. And notice that these time scales get very compressed. Right now, we go from 0 to 10 billion years, and you can see the sun is gradually getting more luminous. But then at 12 billion years, it leaves the main sequence, becomes a red giant, undergoes this helium flash, becomes much less luminous. And when it does the helium flash, it's 1,000 times more luminous than the sun is now. And then goes through a subgiant stage, and then it ejects a planetary nebula. When it does that, it's on the order of 2,000 times more luminous than it is today. And then it transitions to a white dwarf, and its luminosity drops way down. These are some examples of what maybe the sun will eject when it undergoes the central star of a planetary nebula phase. Maybe we'll get this beautiful ring of material that's lit up by the ultraviolet light then coming off of this very hot sun. Here's another example of a planetary nebula. At the end, the sun will be the size of the Earth, and yet still have most of the mass it originally had. The luminosity will be 10,000 times less than what it is now. Now, I'm going to back up for a moment and talk about something I just briefly mentioned, which was I mentioned that during the helium flash, that carbon was created. So you can take 3 helium atoms. We're talking about how you take 4 hydrogen atoms and turn them into 1 atom of helium. You can take 3 helium atoms now and turn them into 1 atom of carbon by having even higher temperatures and a lot of helium. But there's more to it than this. Let me now introduce Margaret Burbage, Jeff Burbage, Willie Fowler, and Sir Fred Hoyle. Now, I've been talking about people who, to me, so far, have been pretty much long time dead. But Jeff Burbage actually was the guy that hired me for my first tenure-track job at Kitt Peak. I was a tenured astronomer there for 20 years. But Burbage was director at the time, and he hired me. Dr. Fowler was somebody I saw walking around campus when I was an undergraduate at Caltech. When I was in high school, Sir Fred Hoyle was writing science fiction books that I enjoyed reading. So these 4 astronomers and physicists wrote a remarkable paper in 1957. There actually is stellar evolution in the biological sense, in that what Margaret Burbage in particular found was that older stars contain fewer, heavier elements than the younger ones. Remember, we talked about metals, how stars were mostly hydrogen and helium, and 1% a little bit everything else. Well, that 1%, sometimes it's 2%, sometimes it's 0.5%. So that percentage, the older stars contained much fewer fractions of these heavier elements than younger stars like the sun. And to these 4 astronomers, this suggested that the elements were being manufactured in stars, right? That would make sense. What if all you needed was hydrogen and the right conditions in the Big Bang? Could you make all of the elements that way? And what they worked out in this paper was that you could. They could explain, they could describe the conditions you needed to create all of the atoms in the universe. In the advertisement for this talk, I quoted Carl Sagan as saying, to make an apple pie from scratch, you must first invent the universe. And the reason for that is the carbon atoms that make up the apples in that apple pie, the iron in our blood, the oxygen that we're breathing right now in this room. All of these atoms were forged in the center of stars. Main-sequence stars, you have, for the evolution of a more massive star than the sun, the kind of stars that I study and which Catherine Nugent will talk about next week. On the main sequence, what they're doing for most of their lives is converting hydrogen to helium. But also for these massive stars, unlike what happens in the sun, you also are producing nitrogen as a byproduct. A lot of the nitrogen in the universe comes from this production. In helium burning, you convert helium into carbon. The later stages of fusion, when you've run out of helium, you then start burning carbon. And you can produce oxygen, you burn oxygen, you produce neon, and so on, until by the end of a massive star's life, you have this incredible little shells of material. Hydrogen on the outside, helium, carbon, oxygen, neon, magnesium, silicon, iron, each representing a more advanced stage in nuclear fusion. And in this table from Lammers and Levesque, you can see what the products are of various nuclear burning and how long we expect that nuclear burning to go on. In the 15 solar mass star, a star that's 15 times the mass of the sun, we would expect the hydrogen fusion to go on for 11 million years. Not 11 billion years the way it is for the sun, but 11 million years. But by the time you get to neon burning, that's like 9 months. Oxygen burning, 2.5 years. Silicon burning, 18 days. Once you produced iron, you have a problem. Nuclear fusion involving iron is endothermic rather than exothermic. What happens is the star implodes, turning into what's called a core collapse supernova. I think this is a good place to end. Let me call your attention to a wonderful viewing opportunity for you who want to learn more about this. You should look at the original Cosmos series, the one that Carl Sagan did, and in particular, the episode called The Lives of the Stars. And I have here the YouTube link for you to copy down or try clicking on. He'll describe things a little bit differently than I did. Some things we've learned in the intervening 20 or 30 years since he made this wonderful program. But he goes into much greater detail than I've been able to do today. So I'm happy to take any questions and just put them in the chat window. And in another 30 seconds or so, I will see those questions. And I've been told that I need to just keep talking for a little while until these questions begin to appear. So that's what I'm going to do. But apparently not very well. So are there any questions? So far, I have nothing coming in over the chat window. Okay. I'm also happy to answer questions by email. You can email me at Massey, M-A-S-S-E-Y, at Lowell, L-O-W-E-L-L.edu. And again, I encourage you to tune in next Tuesday when Catherine Nugent will be talking about Wolf-Rayet stars. So here comes one question. How did we get the elements heavier than iron? Thanks for asking that. That's an excellent question, and I forgot to say this. Is part of the supernova explosion, these heavier elements, all the way up through uranium, are manufactured as what happens in this big implosion in the core of a supernova. Other questions? To me, in preparing for this, one of the things that I found most astonishing was how much we knew even in the late 1600s and 1700s. That given that the invention of the telescope was only in sort of the early 1600s, mid 1600s, I thought that's remarkable. What's the greatest mystery, or this is a question from Michael West, what's the greatest mystery or uncertainty in our understanding of how stars shine today? Ooh, that's a really great question. One of the things that I like about working on stars rather than on the sun is that with the sun, you can see an embarrassmently high amount of detail. Those of you who watched Jeff Hall's excellent talk last Tuesday on solar cycles and stellar cycles understand how complex a star actually can be. One of the mysteries in the field that I work on, mostly the evolution of massive stars, is how much it matters how much material you lose from the star due to stellar winds pushing off the material. The stars I work on are so incredibly luminous and so incredibly hot that radiation pressure pushes off their outer layers, stripping out the hydrogen-rich outer material. But you can also accomplish the same thing by having two stars in orbit around each other in the binary. And so one of the most controversial issues in the subject of massive star evolution these days is what fraction of the evolution is controlled by binarity and having the gravitational influence of one star affecting the other star, and how much of it is what you would have by just having a star by itself. Here's an excellent question. What are the oldest stars? So the oldest stars are the ones that are in globular clusters. When the galaxy first formed, there was a big cloud of gas. And as it began to collapse under its own gravity, little clumps would self-gravitate and form clusters, and within those stars, earlier than the rest of the galaxy forming. So this halo of globular clusters surrounds the Milky Way. Some of these are among the most beautiful things you can see through a telescope, like Messier 13, the globular cluster in the constellation of Hercules. Beautiful sight in the telescope. And once our public program is back open, I encourage you all to come up and see M13 through a telescope. And these stars have the lowest percentage of heavier material. They're also by far the oldest stars, on the order of 12 billion years. What is the most common radioactive material that's present after a supernova? I don't know the answer to that, but I'll look into that for you. Well, that seems to be all the questions we have. I want to thank all of you for tuning in and watching this today. I hope you've enjoyed watching it as much as I enjoyed talking about it and putting it together. Thanks very much.